This is a video from section 7.1. It's on integration by parts. The formula says the integral of u dv is equal to uv minus the integral of v du. Now, I want to give you an important note here. The aim in using integration by parts is to get a simpler integral than the one we started with. That's the ideal. So in other words, we want the integral of v du to be simpler than the integral of u dv. So I want to illustrate with the first example what I mean by that. Now, if we take a look at example 1, suppose I had the integral of, we'll do this one, ye to the negative y dy. So I'm going to choose u to be e to the negative y. And I'm going to let dv be y dy. So notice how we have the product of two functions here. So it's a perfect integration by parts problem. Okay. Now du is negative e to the negative y dy. And v is 1/2 y squared. So the integral of ye to the negative y dy is 1/2 y squared e to the negative y minus the integral of negative 1/2 y squared e to the negative y dy. It's not wrong, but do you notice how this integral here is much harder than the original integral over here? And so that leads me to believe that I want to switch my choices. So in other words, if we do example 1, and my example again is ye to the negative y dy, I want to let u be equal to y, and I'm going to let dv be e to the negative y dy. Because here, notice, du is 1 dy, and v is negative e to the negative y. And so if I take the integral of ye to the negative y dy, that's going to be uv, which is negative ye to the negative y, minus the integral of v du, which is negative e to the negative y dy. Now, this is negative ye to the negative y plus the integral of e to the negative y dy. So this is negative ye to the negative y minus e to the negative y plus c. So again, notice the integral of e to the negative y dy is e to the negative y divided by negative 1, and that's where I'm getting that minus from. Okay, and that's how we do example 1. And one thing I want you to notice how this integral here is much simpler than the original. So that meant choosing u to be y was very ideal. Example 2. Suppose I give you this one. Suppose I had the integral of natural log of x divided by x squared dx. Now, I'm going to let u be the natural log of x. And I'm going to let dv be 1 over x squared dx. Now, it's ideal to choose u to be natural log of x because if we let dv be natural log of x dx, finding v isn't so easy. Okay, so natural log of x is a more complicated function to find the antiderivative of. Okay, and so du is 1 over x dx, and v is negative 1 over x. And so the integral of natural log of x over x squared, dx, can't forget our dx. So this is going to be uv, which is negative 1 over x, ln of x, and we're going to subtract the integral of v du, which is negative 1 over x times 1 over x dx. And so this is negative 1 over x, ln of x, plus the integral of 1 over x squared dx. When you subtract a negative, you add. And so, therefore, the integral of natural log of x over x squared dx is negative 1 over x, ln of x, minus 1 over x, right? The integral of 1 over x squared dx is negative 1 over x. And then, of course, we have to add our constant of integration. And that's the answer to example 2. Let's take a look at example 3. Suppose I give you this one, the integral of the arctangent of 2 over y dy. Now, our u should be immediate because it's an integration by parts problem, and if I already knew how to take the integral, I wouldn't need integration by parts. So u is going to be arctangent of 2y. But then that says dv, you can just call it 1 dy. So du is 1 over 1 plus 2y to the second power. By the chain rule, I have to multiply by the derivative of what's inside, which is 2 dy. And v is equal to y. Now, what that says is the integral of the arctangent of 2y dy is uv, which is y, arctangent of 2y, minus the integral of v du, which is 2y over 1 plus 4y squared dy. And so this is y arctangent of 2y minus, now the integral of 2y over 1 plus 4y squared is 1/4 natural log of 1 plus 4y squared plus c. And if you need, we can calculate that integral on the other side. So if I were going to do the integral of 2y over 1 plus 4y squared dy, so this is a perfect u substitution. I would let u be equal to 1 plus 4y squared. Du is 8y dy, and so y dy is 1 over 8 du. And so this is 2 over 8 times the integral of 1 over u du. And so this is 1 over 4 natural log of the absolute value of u plus c. But remember, 1 plus 4y squared is never negative, no matter what I choose for y. So I don't need those absolute value bars, and so it would be sufficient to write 1/4 natural log of 1 plus 4y squared plus c. And so you can see this result came from u substitution, which is what I have over here. And that's how you do example 3. So if we take a look at example 4, Well, suppose I give you this one. The integral from 0 to 1 of x times 3 to the x dx. And so a good choice of u, and by the way, this is a definite integral, so something to keep in mind. So I'm going to let u equal x. And I'm going to let dv be 3 to the x dx. So du is 1 dx, and v is 3 to the x divided by natural log of 3. And so I'm going to go uv, right? So the integral from 0 to 1 of x times 3 to the x dx is, I'm going to get x times 3 to the x over natural log of 3, evaluated from 0 to 1. And I'm going to subtract the integral from 0 to 1 of 3 to the x over natural log of 3 dx. If I plug the 1 in, I get 3 over natural log of 3. If I plug the 0 in, I just get 0. And so I'm going to subtract off, and then here I'm going to get 3 to the x over natural log of 3, but this time I'm going to square it, and then I'm going to evaluate it from 0 to 1. So I'm going to plug the 1 in, and then I'm going to plug the 0 in. And so when I do, I get 3 over natural log of 3 minus, and then in parentheses, I'm going to plug 1 in, and I'm going to plug 0 in for x. So when I plug 1 in, I get 3 over natural log of 3 squared. When I plug 0 in, I get 1 over natural log of 3 squared. And so if I combine, I get 3 over natural log of 3 minus 2 over natural log of 3 to the second. And so the answer here to example 4 is 3 natural log of 3 minus 2 divided by natural log of 3 squared. And it's always a good idea to check with your instructor to see if this answer is acceptable, or would your instructor want you to get a common denominator and put it as one fraction. So that would be a good question to ask. Let's take a look at example 5. Suppose I had the integral of, let's do this one. Suppose I had the integral from 0 to 1 of r cubed divided by the square root of 4 plus r squared dr. So I'm going to do a little trick here for this one, and this just takes time, you know. So I'm going to go from 0 to 1. I'm going to rewrite r cubed as r times r squared divided by the square root of 4 plus r squared dr. This is an integration by parts problem. Perhaps it's a little bit subtle. What I'm thinking about is this. When I look at the derivative of 4 plus r squared, I get 2r, right? Well, this looks pretty close. And so what I'm going to do is I'm going to let u equal r squared. And I'm going to let dv be r divided by the square root of 4 plus r squared dr. And so du is 2r dr, and v is going to be the square root of 4 plus, here, let's rewrite that. It turns out that v is the square root of 4 plus r squared. And this is one, make sure you're convinced of that. When you take the derivative, remember that this is equal to 4 plus r squared to the 1/2. So when you take the derivative, you get 1/2 of 4 plus r squared to the negative 1/2, but then you're multiplying by 2r, and the 1/2 and the 2 will cancel, and you're just left with that r. So it turns out v will be square root of 4 plus r squared. And so I'm going to go uv. So it turns out that the integral from 0 to 1 of r cubed over the square root of 4 plus r squared dr is equal to, I'm going to go r squared square root of 4 plus r squared, but I'm going to evaluate from 0 to 1, and I'm going to subtract the integral from 0 to 1 of 2r square root of 4 plus r squared dr. If I plug the 1 in, I get square root of 5. If I plug the 0 in, I get 0. So I'm going to get the square root of 5 minus the integral from 0 to 1 of 2r square root of 4 plus r squared dr. So this is square root of 5 minus. Now, this integral, I claim, will be 2/3 times 4 plus r squared to the 3/2, evaluated from 0 up to 1. So this is square root of 5, and then I'm going to subtract off the quantity. If I plug the 1 in, I get 2/3 times 5 to the 3/2. If I plug the 0 in, I get 2/3 times 4 to the 3/2. And so this is square root of 5 minus 2/3 times 5 to the 3/2 can be written as 5 root 5. And then I'm going to add, square root of 4 is 2, 2 to the 3rd is 8, 8 times 2 is 16. So that's 16/3. And so this is 16. And then getting a common denominator, I'm going to subtract 7 root 5, and then I'm going to divide by 3. And that would be the answer for example 5. Let's see if we can do one more example here. This one's pretty good. We'll call this example 7. Or excuse me, example 6. Suppose I had the integral of, well, we'll go from 0 to pi of cosine x times hyperbolic sine of x dx. So this is how I attack. I'm going to let u be the hyperbolic sine of x. And I'm going to let dv be cosine x dx. So du is hyperbolic cosine x, and v is equal to sine of x. And so I'm going to go uv minus the integral of v du. And so this is equal to sine of x, we'll do sinh x, hyperbolic sine of x in other words, times sine of x, but I'm going to evaluate from 0 to pi. And I'm going to subtract the integral from 0 to pi of sine of x times hyperbolic cosine x dx. Now, if I plug pi in for x and plug 0 in for x, this is 0. And so I get 0 minus the integral from 0 to pi of sine of x times hyperbolic cosine x dx. Now, what you want to do is make sure that you're consistent the whole time. So if I'm differentiating the hyperbolic, I want to continue to do that when I do integration by parts again. So we're going to look at negative the integral from 0 to pi of sine of x times hyperbolic cosine x dx. And so again, let's remind ourselves, we're going to differentiate the hyperbolic. So I'm going to let u be hyperbolic cosine x. And I'm going to let dv be negative sine x. Don't forget the negative there, right? So du is hyperbolic sine of x, right? The sign doesn't change when you're dealing with hyperbolics. When you take the derivative, let me be specific. When you're taking the derivative of hyperbolic cosine x, you don't have to worry about a sign change. Now, over here, if dv is negative sine x dx, then v is cosine x. And so I'm going to go uv, which is hyperbolic cosine x. Let's try that again. So we're going to get hyperbolic cosine x times cosine x, evaluated from 0 to pi. And then I'm going to subtract the integral from 0 to pi of cosine x times hyperbolic sine of x dx. If I plug pi in for x and plug 0 in for x, I get, now, when I plug in pi, I get negative hyperbolic cosine of pi. If I plug in 0, I get minus hyperbolic cosine of 0, minus the integral from 0 to pi of cosine x times hyperbolic sine of x dx. Now, here's the goal. We got to put everything together. Now, it turns out, let's see if we could write everything down. The integral from 0 to pi of cosine x times hyperbolic sine of x dx is equal to this integral down here. So let's write that down. The integral from 0 to pi of, well, let's find it again. Cosine x times hyperbolic sine x dx is negative the integral from 0 to pi of sine x times hyperbolic cosine x. But we went through all that work to figure out what negative the integral from 0 to pi of sine x times hyperbolic cosine x is. So that's going to be equal to negative hyperbolic cosine of pi minus hyperbolic cosine of 0. And then I'm going to subtract the integral from 0 to pi of, here, let's create some room. So here, let's come down here. So the integral from 0 to pi of cosine x times hyperbolic sine x dx. This is going to be, now, so this is negative hyperbolic cosine of pi minus hyperbolic cosine of 0 minus the integral from 0 to pi of cosine x times hyperbolic sine x dx. And so I'm going to add that quantity over to the other side. And so I get twice the integral from 0 to pi of cosine x times hyperbolic sine of x dx. And this is going to be negative hyperbolic cosine pi minus hyperbolic cosine of 0. And if I divide by 2, I'm done. So the integral from 0 to pi of cosine x times hyperbolic sine of x dx is 1/2 of negative hyperbolic cosine of pi minus hyperbolic cosine of 0. And I do have to let you know, so hyperbolic cosine of 0 is e to the 0 plus e to the negative 0 divided by 2, which is 1. So your instructor might want you to know that. And so if that's the case, you would probably want to write it this way. So the answer would be 1/2 of negative hyperbolic cosine of pi, that's not friendly, minus 1. And that problem was example 6. And that'll conclude this video for section 7.1, where we did integration by parts, and specifically we did 6 examples. Okay, thank you.